Hi everyone, my name is Saber Tlukdar, and today I'm going to be talking to you about Totem, also known as Tokenized time series embeddings for general time series analysis. This work was done with the wonderful Isong Yu and Georgia Jaksari at Caltech. Before I start, I want you guys to actually think about your favorite time series. There's so many of them and there's so much diversity in this domain. It shouldn't be a hard ask. But if you do need a little bit of inspiration, perhaps you can think about the weather, or the insects that are feeding in your backyard. Maybe you even care about the electricity in the power grid, or the neural signals that are coming out of your brain. A really interesting thing that we could care about is predicting the next big earthquake, or even behavior in galaxies that are very far away. Because there's so much diversity in the time series domain, there are many tasks to actually accomplish, such as imputation, where I have a signal that's corrupted and I basically want to fill it in. I could also care about forecasting, where I'm given some amount of time and I want to know what's going to happen in the future. Or even anomaly detection, where there's something weird in my signal and I want to identify it. Or classification, where I've got some set of sensors and I want to know, am I moving or am I resting? Or even translation, where I have access to some sensors, but I might be missing others, and I want to know what's happening on those sensors that I don't see. Now, there are so many time series, and actually with Totem, we've addressed over 30 real-world data sets spanning over 20 domains across these 5 tasks. Now, this is a lot, and so don't worry, we're not going to cover all of them today. We're going to build up to this. And so what I want to start you with is the real question. So what is the question that really motivates this talk? The next thing we're going to look at are some modern machine learning ingredients, followed by VQVAE tokenization. Don't worry, we're going to build up to this slide as well. Then we're going to check out some codebooks, understand tokenization inference, look at many tasks, and then finish up with some results. Don't worry, we'll build all the way up to here. All right, let's start with the real question. The real question is, can we model time series which evolve continuously with modern machine learning methods in a general manner for many tasks? Now, this was a mouthful, so let's decompose it a little bit. I want to care about the modern machine learning methods, the general manner, and the many tasks. Okay, why? The real question is that we want a methodology that scales, jointly trains across many domains, and works for many tasks. So we want all of these things, which is why we should care about these dimensions. Now what I want to do is I want to take this question and I want to look at it visually, and maybe we can understand and fill in those gaps that are perhaps still there. So the first thing I want to do is I want to understand, how can I take many different domains such as electricity, traffic, and weather, look at the time series from all of them, find some representation, which might look like this, and then look at them with many tasks, such as imputation, forecasting, classification, translation, and anomaly detection. Now what I want to do is I want to take these modern ML methods, general manner, many tasks, and use this color scheme to code in this visualization to help understand a little bit more. And so let's start with the general manner. And so that's going to look like, how do I take all these domains and actually process them into their time series, and how do I actually learn a representation in a general manner? When it comes to many tasks, that's pretty self-explanatory. I want to take this representation and I want to learn with many tasks. Finally, when we want to talk about these modern machine learning methods, the question becomes, how do we actually learn a representation in a modern way? And so for that, we're going to be using the VQVAE right here. And then also, how can I model all of these tasks right here using modern methods? Hopefully, this visualization helped fill in any gaps that you have. Now that we've covered the real question, let's talk about some modern machine learning ingredients. Now, there's a lot of important ingredients, and I'm not going to cover all of them, but we're going to talk about 4 that are very significant. Let's start with a discrete data representation. And all this means is that my representation lives in a fixed space. The next we're going to discuss is the transformer architecture. This is pretty self-explanatory. All this means is, am I using a transformer or not? Next, I want to talk about generalist training. And as a reminder, this means that I'm jointly training on many data domains at once. Lastly, I want to talk about tasks. Now, there's a little bit more nuance in this dimension. The best would be when we have many tasks and we can solve them with unified modeling. The middle would be when we have many tasks, but we're solving them with independent modeling. And the minimum would be where we're only looking at one task. Now what I want to do is I want to map these four back to the criteria we were looking at, which is modern machine learning methods, general manner, and many tasks. Now, as we move forward, I want to actually look at some more developed domains, such as vision and language modeling. And because these domains are more developed, perhaps there are lessons that we can actually learn and then apply to time series. And so what we're going to do is we're going to start with text, images, and video. And we're going to understand how do they size up across these four dimensions. And so with text, images, and video, indeed they are learning discrete data representations. Indeed they use a transformer architecture. And indeed they are trained in a generalist manner. Now when we look at tasks, text actually does have many tasks that are solved with unified modeling. And in images and video, it's a little more complicated. Oftentimes you have a big model just for segmentation, or just for generation, or just for object detection. And having this unified modeling is a little more challenging. Now what I want to do is I want to talk about many different time series methods, and so I'm switching it up a little bit. The far left column is now going to be a method, not a type of domain. And so we're going to start with Totem, and the way that we size up is very similar to images and video, where we're looking at and using discrete data representations, we're using a transformer architecture, we're doing generalist training, and we have many tasks, but we're not necessarily solving them in a unified way. So perhaps this is actually not that different from prior work. So what I want to do is I want to put up two pieces of prior work. We're not going to dive into them in depth, but we just want to see across these four dimensions, how do we size up? So with some prior work, we can see that people have used discrete data representations and people have used transformer architectures, but maybe we haven't explored this generalist training or many, many tasks. Now the next thing I want to do is I want to look at some concurrent work, and I want to understand whether or not these four dimensions are even a direction that people care about. And so we're going to look at Google and Amazon's most recent models, and we can see that indeed they care about this generalist training. And so we can see that even though time series modeling is more nascent than text, images, and video, we are trying to fill in this grid, and we are trying to work towards generalist training on multiple tasks, and eventually we're going to get to unified modeling. Now that we've covered some modern machine learning ingredients, I want to talk to you about VQVAE tokenization. And don't worry, we're going to build up to this slide. So to start with, we have some time series that we're passing through an encoder to get to some continuous representation. Now let's look at this in a little more detail. What the encoder is doing is it's taking the input time series, it's breaking it into chunks, each of compression factor, where the compression factor is of length f. This is a hyperparameter that you get to set. And then it is learning this d-dimensional representation, and I can have as many d-dimensional vectors as I want. Because I can have as many d-dimensional vectors as I want, this is in a continuous space. What we're then going to do is we're going to take this continuous representation, we're going to pass it through a discrete codebook where I can only have k d-dimensional vectors to actually discretize this representation. And what that looks like is this, and add a little more detail, it looks like this. And so I'm taking this green representation, which let's see right there, where this is in my continuous space. I'm passing it through my codebook, which can only have k possible tokens, to get to this discrete representation. And this might be the lookup, so ID number 16, which looks up into this codebook to get this d-dimensional representation. Now I want to emphasize that everything I've just highlighted right here all corresponds to the same data. Now what I'm going to do is I'm going to pass this discretized representation through my decoder to get my time series output. Hopefully that made sense. If it didn't, that's all right. Now we're going to look at some losses very quickly to understand how we're actually training the VQVAE. So the first is a reconstruction loss, then a commitment loss, which forces the encoder to actually commit to some of its representations. And then we've got a codebook loss, which forces the codebook to get to a better discrete fixed representation. Great. Now that we understand the VQVAE at a high level, what we're going to do is I want to show you what it might look like in a horizontal representation, which is what we're going to use for the rest of the talk. And we can look at specialist training with our electricity data set. So we've got electricity time series over here, and then we are reconstructing that electricity time series here. Hopefully, the question that you're now asking yourself is, but Sabera, I thought you said in a generalist manner. I'm so glad that you asked. So in order to understand how we can adapt this whole thing to work in a generalist manner, we have to understand a little bit more about time series data. And so to do that, we're going to use electricity. Now, most time series data is organized by S sensors, T time steps, and E examples. And we can actually apply the VQVAE across any of these dimensions. So the sensor dimension, the example dimension, or the time series dimension. And we can actually apply the VQVAE in chunks. It doesn't just have to be across one dimension. It can be a tensor across this whole bigger tensor. However, when we think about what we want to do with these codebooks, if we want to train and or test in a general manner, we might also want to work with traffic data or electricity data. Now, traffic data and electricity data will certainly have different number of sensors, and those sensors are going to mean completely different things, and they might have a different number of examples. And those examples might not even correspond to the same amount of time. For instance, in electricity, a sample might be for 1 day, an example might be for 1 day, and in traffic, an example might be for 1 hour. So because we want to train in this generalist way, we're going to apply the VQVAE across this time dimension. And so all that means is that I'm going to reorganize my data such that it's T by S by E. Another important piece that we have to apply is some normalization. So for each example, we're going to subtract the mean and divide by the standard deviation. What this enables us to do is actually separate the notion of waveform and scale. And so what we're going to do is we're going to learn these codebooks in this waveform space that's scale independent. And if we care about incorporating scale, we can reintroduce that mean and standard deviation later in our downstream modeling. Now that we understand some of the design decisions that might enable generalist training, let's see how we can adapt our specialist VQVAE to work generalist. So as I mentioned, because of those design decisions, as well as some others that we're not going to talk about here, but what we will discuss in the paper, so read it if you want more information, all we have to do is actually just use generalist data. And so we're glad that we considered the notion of generalist training and actually also testing. So now that we have some understanding of how the VQVAE will work in both of these settings, let's talk about some codebooks. Great. So what we're going to do is we're actually going to fix our representation, and we're also going to fix our decoder. And the reason we want to do this is because we want to take our codebooks, pass them through the decoder, and look at what they are in time space. And so in everything I'm about to show you, we're using 256 code words. And what we're going to do is we're going to look at some of the specialists and our generalist. Great. So let's start with our electricity data set. So here we're looking at all 256 code words. We're using a compression factor of 4, so times 0 through 3. And we're in some normalized space, so we've got some magnitude. I've highlighted one code word here, and I'll explain why it's highlighted later. Don't worry about it for now. And so we've got 256 code words. I've randomly highlighted one. Let's look at what this looks like for weather. And so again, we have slightly different distribution, and we've got one code word that I've highlighted. I'll explain why later. And then lastly, we can look at our specialist traffic codebook. And the distribution's a little bit different. The shifting of magnitude's a little bit higher, but that seems reasonable. And again, I've highlighted one code word here, and I'll discuss why in a second. So what we hope is that when we move to the specialist codebook, we don't want to see a smoothing of all of these modalities. We still want to capture motifs of our specialists in our generalist. So let's see if that's actually true. So this is what the distribution of our generalist looks like, so here. And what I've done, let's say with this green example, is I've taken this one randomly. I've looped through all 256 of my specialist code words. I've picked the closest one. So that would be this green one right here. And I've done the same thing in my weather data set and the same thing right there in my traffic data set. And so what this is showing me is that even when I'm doing generalist modeling, I'm not smoothing across all my domains. I am indeed retaining some motifs that I see in my specialist. Now that's great. And it's great that we have a code book that can actually capture all of this information. Now what I want to do is I want to look at a case study. It's really hard for humans with our tiny little brains to think in this 256-dimensional space and actually see all the patterns. So for this data set, just for the purposes of visualization, I've dropped it down to only use 10 code words for a very, very repetitive data set. And what I want to see is that we have sequences of tokens that capture trends in time series. And if we can do that, then I've convinced at least myself that sequences of tokens can capture these repetitive notions. So let's dive in. In this insect feeding data set, we can see the rhythmic nature, and I'm actually going to highlight A, B, C, and D. These are just an inflection that appears, and I've just picked 4 points of this time series to inspect a little further. So what I'm going to do is I'm going to zoom into A, and I'm going to see what are the tokens that it's using to represent this time series. And it's looking like it's using token sequence 057. And now let's zoom into B. And even at B, the time series, it looks pretty similar. So A looks like this, B looks like this, so they're pretty similar. And it's also using 057. Now I want to look at C, and I'm seeing 059. Now this is perhaps some cause for concern, but maybe it's fine. Maybe it's just a blip. Let's look at D. And in D, I'm getting 059. And so all of these trends, they look pretty similar, so this might be a little bit concerning. But before we freak out, let's go look at what 7 and 9 look like in our decoded time space. Thankfully, 7 and 9 look really similar. So they're both doing this general upwards trend. 9 has like a little bit more of a kink in it, but it's doing the same trend. And so it makes sense why, let's see there, 7 and 9 could be used interchangeably. And so this is great. Now I've demonstrated that we can have sequences of tokens, and these sequences of tokens can capture these periodic signals and these periodic signals as they evolve across my time series. Now that we've discussed codebooks, let's go into a little bit more detail about tokenization inference. And we actually don't need that many slides to describe it. So once I've trained my VQVAE, and let's say in my generalist and my specialist, I've trained both of them using weather. For in-domain inference, I would take my weather data set, some held out test set, tokenize it, and then see what the performance might look like. And so this is in-domain because I've trained with it. Another thing we can do is look at data sets that we've never actually seen before. So US birth, neuroscience, and river flow were not used in training. And when we actually perform with them, we're doing zero-shot inference. Moving forward, let's talk about the many tasks. And so this is going to be a lot. I'm not going to go into detail about every single method, but I want to give you a taste of what we can do with them. And so I want to remind you that we're working with a representation that's locked. So it doesn't matter what I do in my downstream task. This representation does not update based on forecasting or classification or any of those. It's just trained using the VQVAE and then fixed. So I actually want to start with the simpler ones, which are imputation and anomaly detection. And imputation and anomaly detection, they do not require any downstream modeling. So let's actually explain why. So you should be very familiar with this VQVAE layout by now. To solve the imputation task, all I need to do is instead of inputting clean data, mask my data, and then train the VQVAE to do reconstruction and imputation. So simply by adding masking into my input data and having the output be this data right here, which is clean, I've used the VQVAE to solve imputation as well as reconstruction. So that's pretty handy, pretty straightforward. Now let's dive into anomaly detection. With anomaly detection, I've got my VQVAE set up and I've got my frozen codebook set up. And so what I'm going to do, importantly, is I'm only going to train with clean data. This is very important. The next thing that I'm going to do is at test time, I'm going to use anomalous data and pretend there's 25% anomaly that's in my test set. So with this anomalous data, we're getting 4 tokens, so 16, 243, 7, 91, and pretend those tokens correspond to these chunks in time series. So what I'm going to do is I'm going to take this token, I'm going to compare it to my input, and that looks like it would have a pretty similar mean squared error. Next, I'm going to look at this token, compare it to this one, that one right there, and that doesn't actually look that similar. Then if I look at the 2 last ones, these are pretty similar to my output here. However, I know that there's 25% anomaly in my test set. So I'm going to say that the worst 25% of my tokens correspond to the anomaly. And that would look like this, where that red chunk is the anomaly. Now you might be thinking to yourself, but Sabera, what if in the test set I don't know my percent anomaly? And you're totally right, this setup would not work if you don't know your percent anomaly. However, we have made some adaptations that would enable this. However, most benchmarks are actually set up to work like this, so for now, that's what we're going to stick with. Moving forward, let's actually look at the more complicated tasks. And what we're going to do is we're actually going to use 3 components that we mix and match to solve translation, classification, and forecasting. What are those components? So those components are the time series transformer encoder, the scale reinstator, and the sensor transformer encoder. So the time transformer encoder is going to learn the relationship of tokens across time. The scale reinstator is going to reinstate that mean and standard deviation that we previously removed from our codebook. And then for the sensor transformer encoder, it's going to learn the relationship across the sensor dimension. So let's, at a very high level, look at translation. With translation, everything that's in this dotted box is what the model has access to. Everything outside the dotted box, namely the time series up in that corner, the model does not have access to. So the task is basically to take tokens corresponding to sensors that I have. I don't have some of the sensors. Take these tokens and then tell me the sensor information that I was not given. So that's translation. I have some sensors, I don't have others, and I want to understand what those sensors are. Classification is actually very similar to translation. The only difference is that the input time series is complete, so I'm getting all of my tokens up here, and then I might have some task like telling whether or not I'm moving or resting in a data set. Now let's dive into forecasting. Now with forecasting, we're going to go into a little bit more depth so that you guys can understand this model at a little bit lower level of granularity. And so tokenization, what I'm given is some time series up here, and I have a look back length, which in that upper left corner is in dark green. And so I'm going to give all of these tokens, which correspond to the tokens for my look back length, to my forecaster, which is using a transformer encoder for time, and then a scale reinstator. And then that's going to predict directly in time my look ahead length. And when I put this with the input I've been given, this is my forecast. So let's look at this at a little bit lower level of granularity. And so here what's happening is I've got my time series, I'm tokenizing it with my pre-trained codebook, and that gives me these tokens here. So everything right here corresponds to everything that's right here. Okay, the next thing I'm doing is I'm adding a positional embedding, so 0, 1, 2, 3, and this corresponds to the ordering in time. This gets passed into my transformer encoder, which then goes to a linear layer. And that corresponds to this, whoops, right there, this time transformer encoder. Then what I'm going to do is I'm going to have a linear layer that predicts my future mean and standard deviation. So we have to do this because our codebooks are learned in this normalized space, and I want to reintroduce that scale information. And so that corresponds to our scale reinstator right there. And to make this a little bit more explicit, these are the arrows. So hopefully, if my explanation didn't do it justice, the arrows will. Now that we understand forecasting at a little bit more depth, I want to mention that if you don't want to do transformer modeling, perhaps you don't have the compute to do it, or perhaps you want to use simpler methods because you care about interpretability, we have also shown that you can solve a forecasting with the MLP, and an MLP plus tokens actually works better than an MLP with a more naive time series representation. So even if you want to use simpler modeling techniques, I would say tokens are still the way to go. Now that we've looked at many tasks, let's look at some results. So to start with, I want to look at the generalist codebook. I want to know, is the generalist codebook doing a good job of representing all of this diverse data? And so I want to say that it's not obvious that a discrete set of tokens will performantly represent continuous time when jointly trained on many data sets. This is not clear. And the only way I'm going to get at this is by seeing what is the error of my generalist codebook. And so I want to start with that. So what we're plotting here is generalist codebook mean squared error across many data sets. And my MSC, it's a little bit lower than 0.025. Now that seems low to me. That seems like that's not a lot of error, but it really only matters in relation to my downstream tasks. And ideally, I want the error on these downstream tasks, I want the error from this generalist code book to be a lot smaller than the error from my downstream tasks. So what I'm going to do is I'm going to look at the easiest possible generalist task, which is generalist imputation at 12.5%. And that looks like this. And this is great because this error here is smaller than most of the errors up here, which means that my generalist is actually doing a pretty good job of representing many data sets all at once. Now what I want to do is I want to look at the easiest forecasting task. And this is just magnified. The error here is really small compared to the errors up here. So this is really demonstrating that these tasks are very challenging. However, my error, most of it isn't actually coming from my representation, and this is great. I also want to mention that for the specialists, this is the same trend. The code books for the specialists, the error from them is very small compared to the error from the downstream tasks because these downstream tasks are really complicated. Next, I want to look at the specialist in-domain results. And as a reminder, this is the VQVAE from the specialist. I'm just training on one data set. And then for my downstream task, I'm also going to only train on one data set. So I'm first going to look at imputation. And with imputation, as well as all the other tasks, there's many different versions of this task. So with imputation, we've done 12.5% all the way up to 50% with a few in between. And we've done this on many data sets. So across all the tasks, what I'm going to count is actually how many times across all the variations of this task across all of the data sets does Totem win compared to other models. And we've done this on many of them. I'm just going to put up a few to make it easier to present. So in imputation, in the specialist in-domain, Totem wins 52.1% of the time, followed by GPT-2 at 35.4%. For anomaly detection, Totem wins 33.3% of the time. For forecasting, Totem wins 28.6% of the time. Now let's actually look at the generalist in-domain. And as a reminder, the generalist VQVAE looks like this, and the in-domain testing is from a held-out test set, which was also in-domain. Now for imputation, Totem is at 58.3%. For anomaly detection, Totem's at 80%. For forecasting, Totem is at 67.9%. Now what I want to do is I want to look at the hardest task, which is zero shot. So again, we're going to be using our generalist VQVAE, and we're also going to be using our generalist downstream modeling, but we're testing on these zero shot test sets that I've never seen before. For imputation, Totem wins 80% of the time. For anomaly detection, 73.3% of the time. And for forecasting, 90% of the time. Now that's great, but what does all of this mean if I don't show you what the outputs and the examples actually look like? Great, so let's look at imputation for electricity. So in imputation, what I'm doing is I'm setting some of this data to 0, so that's why it looks really jagged. And then I have my ground truth and I'm comparing it to my prediction from the top. And so as we can see, the prediction is doing a really good job of matching the ground truth. Let's move on to forecasting. So here in forecasting, we've got our input in gray, our ground truth again in green, and then our prediction in pink. And so what I'm seeing here is that the ground truth in the middle is actually a little more jagged, and the prediction is doing a good job of following the mean, but maybe not capturing this higher frequency information. Now, if that's what we care about, we can actually adapt the model to capture this high frequency information. But honestly, our prediction is doing a really good job, and following this mean for most use cases is good. Now what I want to look at is zero-shot translation. And to explain these results and to explain this example, I have to tell you a little bit more about earthquake data. So with earthquake data, each sensor actually records 3 directions of movement. There's east-west, north-south, and vertical displacement. And so what I'm going to give my model is I'm going to give my model east-west, north-south, and then I'm going to ask it to tell me what's happening for the envelope of my vertical translation. And so here we can see the ground truth and we can see the prediction. And what we're seeing again is similar to forecasting, where we're doing a good job of finding the mean, but maybe not as good a job of capturing the high frequency information. But again, we can adapt the method to actually capture this information if that's what we really care about. Now that we've seen examples from a few different use cases across a few different data sets and tasks, I want to thank you guys for your attention, mention that you can check out more details about the method on arXiv and/or get the code on GitHub and start working with it on your own and with your own interesting time series problem. Thank you guys so much for your attention, and I'll see you next time.